Dodecahedron is a convex polyhedron where each of the 12 faces is a rhombus, and all of the faces are congruent to each other. The number of edges that meet at a vertex is either 3 or 4, depending on the vertex. What is the number of vertices at which exactly 3 edges meet? Okay, so let's assume that there are, I'm going to assume that there are A vertices for which 3 edges are intersecting, and there are B vertices at which exactly 3 edges are intersecting. Now, the very first thing that I'm going to count is the number of edges. Okay, so how many edges do we have? On the one hand, each first type vertex contributes 3A, and the second type contributes 4B edges, but each edge is counted twice because each edge has 2 vertices, so we need to divide it by 2. This has to equal to, we have 12 faces, 12 rhombuses, each has 4 edges, but each edge is counted twice because each edge is an edge of 2 different rhombuses. Okay, so we need to divide it by 2, right? And then this is indeed 24. Okay, so the first equation for A and B is 3A plus 4B equals 48. Okay, so let's keep this equation in mind. Let's call it the first equation. And we're going to use Euler's theorem to get the second equation. So let's recall Euler's theorem. It states that in a 3D object, the faces, number of faces minus number of edges plus number of vertices always equals to 2. So, or in other words, number of 2D objects minus number of 1D objects plus number of 0D objects always at 2. Right? Let's use this formula, substitute what we know. So we know that there are 12 faces. And how many edges are there? We already calculated it. It's 24. And how many vertices do we have? In total, we have A plus B vertices. So let's write A plus B here. And these add to 2. And this way, I can find A plus B equals 14. And let's call it our second equation. Now we can use the first and the second equation to solve for both A and B. I'm going to make a shortcut. I'm going to multiply this by 4. And then then I get 4A plus 4B equals 56. I'm going to subtract first equation from my last equation to obtain A equals 56 minus 48 equals 8. And A actually counts the number of vertices at which exactly 3 edges meet. So our answer is 8, which is D.